Hello everyone and welcome to CAD/CAMC tutorials. In the previous video we have developed a MATLAB code for a 2D steady state heat conduction problem where one of the wall is having an adiabatic boundary condition while the other three walls are having a constant temperature boundary condition. In this video we are going to perform a steady state simulation using the ANSYS Fluent software, and we'll use the same problem statement where left wall and bottom wall of the domain are at a higher temperature of 120 degrees centigrade. The top wall is having a lower temperature of 40 degrees centigrade while the right wall is having adiabatic boundary condition. So in this video first we will perform a simulation using the ANSYS Fluent. We will obtain the results and then we will try to compare the result of our MATLAB code with the ANSYS Fluent results. So let's begin with the ANSYS. So here you can see the workbench window where we are having the project schematic as well as we are having the different analysis systems in the left side. So here we'll be using the Fluent to solve this problem. So click on the Fluent and drag it into the project schematic. Now in order to perform the simulation we have to follow the series of the processes where first we'll create the geometry, that is nothing the domain. The second one will be the discretization of domain, that we will do it using the mesh generation. Once the mesh is generated, we'll go for the boundary condition using the setup and then we'll solve the problem. Once the solution is there, we'll post-process the result using these results. So let's start with the geometry creation. So we'll right click on the geometry and select here new space claim geometry. Once we'll click on this, another software will be open, that is the ANSYS space claim, and that is used to create the geometry for the different simulation problems. So here we can see the ANSYS space claim software. So first we have to select the plane on which we want to create the sketch. So in our problem it is a 2D problem where we are having a rectangular domain, or you can say a square domain with having zero thickness in the third direction. So first we have to select the plane of the sketch. So we'll select here on this edit button and then we'll select the XY plane. So you can hover the mouse in between the X and Y axis and just click over here. So once you have selected the plane of the sketch, we'll just click on the normal view or the plane view. So once we'll click on this, we will be having the XY plane perpendicular to the screen. Now here we have to create our domain, that is nothing but the geometry. So in our problem we know that the domain size is 1 meter by 1 meter and the shape of the domain is a rectangle. So here we'll go to the rectangle and we'll create a rectangle. So here we'll create a rectangle in such a way that the bottom left corner is at 0, 0. So we'll click over here on the origin and we'll drag like this. Now here we can specify the dimensions of the rectangle. So in our case it is 1000 by 1000. So we'll specify here 1000 mm and press tab, and on the second direction also it is 1000 mm. So we'll enter here 1000 and click on the enter. So here first we have created the domain. So basically it is a sketch. We need to create a 2D domain. So basically a surface that is having no thickness in the third direction. So we can just click on this solid mode or 3D mode. Once you will click on this 3D mode, you can see here a surface is created and we can check it using this structure also. So once you will click on the structure, you will find here one surface, and the surface is nothing but it is having zero thickness perpendicular to the plane of the screen. So in our case also we are dealing with the 2D geometry. So once we have created the domain, that is nothing but the geometry, we have to mesh it. So now again we'll go to the workbench. So we have already created the geometry and you can see here a tick mark, a green tick mark that shows that geometry exists. Now after creating the geometry we'll go to the mesh. So we'll double click on the mesh and the mesh window will open. So mesh is nothing but the discretization of domain where we will divide the entire domain into the small elements. So during the MATLAB code development, we have divided the entire domain into a small rectangles, and we'll do the same in the ANSYS also. So to have the consistency between the developed code and the ANSYS Fluent, we'll use the same parameter for the mesh generation. So now first we'll click on the Z axis, and here you can see the entire domain. So before creating the mesh, let us first give the name to the different boundaries of the domain. And for that, first we'll click on this edge. Then first we'll select here the left wall, right click and select here create name selection. So here this is the left wall, so we'll give it name as a left wall. In the similar fashion, we'll give name to the other three walls as a top wall, right wall and bottom wall. So once we have applied the name for the four walls, we can also apply the name to the entire 2D domain or the entire surface. For that, first we need to click here on the face, select here the entire face, right click and select create name selection. So we'll give it name as a 2D domain and then click on OK. So once the name are given to the different entities of the domain, we can check it from over here from the named selections. So once we'll click on this plus button, you can see all the 5 names that are given along with the type of the feature. So here we can see edges for this 4. Here we can see the surface for this 2D domain. So after giving the name, we need to create the mesh. So first we'll create the default mesh and we'll check whether it is sufficient or not. Right click on the mesh and select here generate mesh. So here you can see it has default created the quadrilateral mesh. So we are having the rectangular elements within the domain. But the thing is that we are not having 100 elements in the x direction and 100 elements in the y direction. Because while developing a MATLAB code, we have considered 101 nodes, that is equivalent to the 100 elements in the x direction, and the same for the y direction. So in order to have the consistency between the MATLAB code and the ANSYS simulation, we'll use the same 100 element in the x direction and 100 element in the y direction. For that, first we have to size the domain. So right click on the mesh, select here insert and we'll go for the sizing. Now here we need to create the geometry for which we want to apply the sizing. So the geometry can be 2D or 3D. Now in our case we want to apply sizing for sides. So we'll select here first this geometry. Then from here we'll select the edge. And now we'll select all the edges one by one by pressing the control button. And once you'll click on any of the edges, it will be converted to the green color so that you will come to know that this edge is selected. After selecting all the 4 edges, we'll just click on the apply button and here you can see it shows 4 edges that we have selected. So for all these 4 edges, we want to apply 100 divisions along the edge. And for that we'll go to the type and here we'll select number of divisions. So number of division is nothing but the number of elements in the respective edge. So in our case we want to create 100 divisions or 100 elements. So here we'll select 100 and in the behavior we'll select the hard. Now again we'll right click on the mesh and we'll create update. And now here we'll click on the mesh to check whether the settings are applied or not. So here we can see that it has divided all the edges into the 100 element, but it is not uniform across the domain. Or basically it is not a perfect quadrilateral. In order to create a perfect quadrilateral within the domain, again we'll go for the mesh, we'll go for the insert and select the face meshing. Now here in this case we have to select the face, so we are not having other options like vertex, edge and body. The only option is face. So here we can select this face, click on the apply and right click on the mesh and select update. So after creating the edge sizing and after creating the face meshing, we can have all the elements as a square that is having the length of 1 meter by 100 divisions, that is 0.01 meter. So this is nothing but the second step of the simulation, that is discretization of domain, or we can say it as a mesh generation. So once the mesh is generated, now we can move to the third step. So again we'll go to the workbench. So here in the flow process you can see here a green tick on the mesh that shows that mesh is generated. Once the mesh is generated, we can go for the setup where we can specify the boundary condition. So here in the Fluent launcher we'll select double precision, and for the processing option we'll select here parallel to make the process faster. Now here we'll select 4 cores or 4 processors and click on OK. So once the Fluent setup window will open, you can see here the mesh that is generated for a 2D domain. Now here in our case we are having the solid domain for the entire problem, so we don't have to create a fluid and we don't have to solve the Navier-Stokes equation. So let us first go for the models. So in our case we just want to solve the energy equation within the domain, so we'll double click on the energy and we'll turn it on. Okay. Now after specifying the models, or basically this model shows what are the different governing equations that you want to solve within the domain. So in our case we just want to solve the energy equation because it is not having any fluid domain. Now after applying the models we have to create, or let's say we have to assign the material to the different parts of the domain. So as we know that in our case it is only solid, and here in the solid the default material is aluminum. Now while deriving the governing differential equation, we came to know that the steady state problem of 2D conduction is not dependent on any of the material. So irrespective of the material, the temperature distribution will be same. So here we don't have to create any specific material and we'll be using aluminum as a material for the domain. Now after having the materials, we have to go for the cell zone condition where basically we have to assign material to the domain. So here we'll select here, double click on this zone 2D domain, and here we can see the material name as a air. So in our case we want a material as aluminum, but here it shows air because air is a kind of fluid. So before applying the material over here, we'll click on the cell zone, and from here we'll select the domain, that is a 2D domain. In the type we'll select here solid, and here we can specify the material. So as we know that the problem will be independent of the solid, so we can select here aluminum and click on OK. Now after specifying the cell zone condition, we have to specify the boundary conditions for all the 4 walls as well as the interior domain. So first we'll go to the boundary condition for the bottom wall. So double click on the bottom wall, and here we can see in the thermal we are having the temperature as a boundary condition. So we know that the left wall as well as the bottom wall is having a higher temperature of 120 degrees centigrade. So we'll click on the temperature. Now here it shows the temperature in the Kelvin. So let us first convert to the centigrade. So click on the units, and here you can press the T from the keyboard, so it will directly take you to the temperature. In the temperature we have to select the centigrade and then we'll close it. Again double click on the bottom wall, go to the temperature. Now the temperature is in degrees centigrade, so we can directly specify 120 for the bottom wall and click on OK. In the similar fashion we can specify the 120 degrees centigrade for the left wall also. So double click on the left wall. Again we'll go to the temperature, and here we'll specify 120 degrees centigrade as a temperature to the left wall. Now we know that for the right wall we are having a 40 degrees centigrade of temperature. So again double click on the top wall, go to the temperature, and the temperature is 40 degrees centigrade. Now we have to apply the boundary condition for the right wall, and we know that the right wall is adiabatic wall, and that means that there is no heat transfer across the wall, across the right wall. So again double click on the right wall. Now here you can see, now we have to specify the heat flux, and that shows that how much heat will enter from the right wall. So in our case we don't want any heat transfer at the right wall. So by default the boundary condition is adiabatic for the fluent, and that shows that heat flux equals to 0 for the particular wall. In our case it is right wall. So we'll keep it as a default and we'll just click on OK. Now once the boundary conditions are given, now we'll initialize the problem. So we'll double click on the initialization and we'll go for the hybrid initialization. So here we can see that the hybrid initialization is done. Now we'll go for the run calculation. So we'll double click on the run calculation. Here we can specify the number of iterations that we want to perform. So here we'll specify 1000 as a number of iteration, or let's say 100, and we'll just click on calculate. So here we can see that the solution was converged within the 4 iterations, and we can see a message of calculation complete. So we can just click on OK. So once the calculation is done, the Fluent is having result, and now we can post process the result using the CFD post. So here you can see the window for the CFD post. So let us first click on the Z axis, and this is our 2D domain. So now let us first try to create a contour and let us check whether it is same or not. So we'll click on this contour, and here we can give it a name as a temperature distribution, or let's say temp distribution, and click on OK. Now here first we have to create the domain. So in our case we'll select the 2D domain and we'll select the interior. So basically it is shown by symmetry 1 and 2, so we can select any one of it. So let us first select symmetry 1. Now here we have to select the variable that we want to plot on this 2D domain. So we want to plot the temperatures, and here we'll keep the range as a global. Now in order to make the smooth contour, we'll increase the rank of the contour to let's say 100 and click on the apply. So here we can see a similar kind of temperature distribution within the domain what we got from the MATLAB code, and here we can see that the left wall and bottom wall is at a higher temperature, the top wall is at lower temperature, and the right wall is having adiabatic boundary condition where the gradient of temperature is 0. So it is a kind of qualitative comparison. Now in order to make a quantitative comparison, what we will do is we'll create a line at the middle of the domain, basically a horizontal line, and we'll take the temperature data at the line and we'll compare the same data from the MATLAB code also. So in order to take the data at a horizontal midline, first we need to create a line, and for that we'll go for the location, we'll go for the line. So we'll give name as a mid horizontal and click on OK. Now here we know that our domain starts from the bottom left corner. So basically it is origin that is having coordinate of 0 0, and the top right corner is having coordinate of 1 because length and height of the domain is 1. So when we want to create a horizontal line that is passing through the mid height, we know that the first point will be having the coordinates of 0 and 500 if we consider it in mm, or 0 and 0.5 in meter. For the second point of the line, we are having the coordinates of 1 and 0.5. So here, to create a line, it shows 3 coordinates for 0.1 as well as 0.2. So as we are dealing in the 2D domain, we don't have to enter the Z coordinate. So for the first point, the coordinates are 0 and 0.5. So let's specify 0 and 0.5. For the second point, it is 1 and 0.5. Enter here 1 and 0.5. After specifying the 2 points for the line, we need to give it number of samples. So basically, number of samples is at how many points you want to collect the data of temperature. So in our case, we know that in the MATLAB code, we have considered 101 node points in the X as well as the Y direction. So when we'll take the data from the MATLAB code, we'll be having 101 points on the horizontal midline. So here also we'll try to take 101 samples or 101 temperature data points. So here we'll enter 101 as a number of samples and click on apply. So here we'll just turn off this contour temperature distribution so that we can see the line that we have created. So this is the line along which we want to take the temperature data from the solution. Once this line is created, we can create a chart or we can create a line graph at this line for the temperature. For that, we'll select here the chart and you can give it any name. So we'll keep it default as a chart1 and click on OK. Now here it shows the title, you can give it any title, and here we want to create a line graph for XY. Basically that is for 2 variable. Now we'll go to the data series and here also we can give it any name for the series. And now important thing is here we have to specify the location. So basically at which location we want to create this data series. So in our case it is mid horizontal because we want to create the data at this line. After selecting the location, we have to specify the X and Y axis. So in the X axis, what you want to give as a distance or as a node point. So in our case, we'll give it as a chart count. And we know that while creating the line, we have specified the 101 sample. So it will use the same chart count that will start from 1 to 101. For the y-axis, we need to select the variable that we want to plot on the y-axis. In our case, it will be the temperature. So we'll select temperature and then we'll just click on the apply. Once you'll click on the apply button, you can see the graph on the screen. And here it shows that at the location of 0 and 0.5, that is basically at the left wall, it is a higher temperature of 120 degrees centigrade. And when you are moving towards the right wall, and you can see near the right wall, the gradient of temperature is 0, and that we can see by this horizontal line. So after plotting this graph, we can export the data to compare the results with the MATLAB result. So we'll just click on the export and here we'll select the desktop. Here you can give any name to the file. So in our case, let us give it as a temperature and ANSYS, and we'll just save it. Now let us extract the temperature points at the same location, and for that we'll go to the MATLAB. So this is the same solution that we got from the ANSYS also. So we'll close this window and we'll run this code again. So click on the run. Once we are having the solution, we'll try to get the temperature at the same location that we have found from the ANSYS Fluent. So once we are having the solution, here we can see an array of temperature that is having 101 by 10 nodes in the X and Y direction. So now in our case, if we want to get the data at the horizontal midline, that is at a mid height, we can imagine that. So for the first point, the I index will be 1, but the J index will be mid of 1 and 101, that is 51. In the same fashion, for the second point, its I index will be 101, but the J index will be same, that is 51. So here what we'll do is, we have to create one variable that will store the value of the temperature at the mid horizontal line. For that, here in the command window we will first create an array of mid horizontal, and we'll assign the temperature value from the array of 101 by 101. So that is the temperature T. Now we'll extract some data points. So what are the points? So basically we have to extract the data point at the mid horizontal line. In that we want to extract the data of all the x point at a y of 51. So at all the x point and y of 51, and we'll just click on enter to see the results. So here we can see that it has created basically one array or one column, and we can check it from here also, mid horizontal. So it shows that it is having 101 rows and one column. So we can double click on this mid horizontal. Now here we can click on this first cell, then we can click on the shift control and the downward key, and we can copy this data. After copying this data, what we need to do is we'll paste this data over here in the Excel. So let us first paste over here. So it is from the MATLAB. Now we need to take the results from the ANSYS also, and for that we'll go to the desktop, and then we'll use this temp ANSYS file. So double click on that. So it will contain the data points for the temperature from the ANSYS. So this first one shows the chart count, and the second one will show the temperature column. So here also we can select all the data points from here. We can copy it and we'll paste it to the same Excel over here. Now the first one you can see it as a node, and second one is from ANSYS. Now we'll take the difference of both of these to see what is the difference between the result of the ANSYS and MATLAB, and for that we'll use the percentage error. So here we'll write down one formula for the percentage error. So that is nothing but the absolute value of the ANSYS as well as the MATLAB, and then we will use here the value of ANSYS as a reference value. So we'll select here the B2 as ANSYS value, and here we'll multiply it by 100 to convert it into the percentage. Now here we can drag it for all the nodes. Now once we have dragged it for all the nodes, we need to check it what is the maximum error between the ANSYS and MATLAB. So here in this cell we'll write down one formula of max that will find the maximum value, and from what cells, and for that we'll select all these differences or percentage errors. And then we'll close it and press enter. So here we can see that we are having a maximum error of 0.046%. So that's it for now. I hope you enjoyed the videos. For the upcoming videos, stay tuned to the CAD/CAM CE tutorials. Thanks.